Hello, I'll be performing a presentation on Quiver representations, Gabriel's theorem, and applications in TDA, or topological data analysis. This reading was performed for my honors thesis, mentored by Dr. Srikanth Iyengar, and I plan to give a brief overview of important definitions in Quiver theory, a short description of Gabriel's theorem, which is an important classification theorem, and then provide a short example of how these concepts are related to persistence theory and topological data analysis. To start, a quiver consists of a set of vertices, a set of edges, a function that gives a starting vertex, and then another function which gives a terminating vertex of an edge. In this sense, it's like a graph, except with arrows. Now, a representation of a quiver is a collection of k vector spaces for some field k, any field k. Each vector space is associated with the vertices, and then linear maps, one associated with each edge. And then all quivers in the first part of this presentation, before the topological data analysis, will be assumed to be finite, and the representations will be finite dimensional. For some examples, we can think of a quiver. Usually, we can write out explicitly what the sets and function are, but usually we just depict them graphically or geometrically. And so in this case, our vertices are 1, 2, 3, and 4, and our edges are alpha, beta, and gamma. And then the arrow gives the direction. We can have more complicated quivers, as in the second example, where we can have loops, which is when an edge starts and terminates on the same vertex. We can also have multiple edges either going in the same or in opposite directions between any two given vertices. For examples of representations, we can take this first example where k is our field, and then the first two vertices have the one-dimensional vector space, and the third has the zero space. And then our first map is the identity, and our second is the zero map. We can also think of a representation of our first quiver example, where we take one-dimensional vector spaces on the outside vertices and a two-dimensional on the inside, and we have linear functions represented by matrices. Now we now have a definition for what quivers and their representations look like. So now we can ask, how can we move from one to another? And the answer is through morphisms. And so for a quiver Q and two representations M and N, we can create a morphism from M to N, which is a collection of k linear maps such that it commutes with the representation functions for all of the arrows. And so in other words, we can start with at our Mi and go through our phi alpha to mj, and then go through our morphism to nj. And we should wind up at the same place as if we started at mi, went through our morphism, and then went through the representations function. This is for all the arrows in our quiver. Our morphism is an isomorphism if each of its linear maps is a bijection. We can also combine representations, and that's through direct sums. So if we have two representations of our quiver Q, then the direct sum, we just take, for the vector spaces, we take the direct sum of the two vector spaces, and for the linear maps, we just take the, direct sum of those maps. And in the case when our vector spaces are finite dimensional, we can just represent them as matrices, but we can also do this if our vector spaces were infinite dimensional. And we can also ask, when can we break down our representations to smaller parts? And so a non-zero representation, M of a quiver Q, is called indecomposable if it cannot be written as a direct sum. So it's indecomposable if we can't break it down into the sum of smaller representations. The question then becomes, if we have a quiver Q and a representation M, how do we know if it's indecomposable or decomposable? And if it is decomposable, what do we know about the structure if we did try to break it down? And some help is given by the Kroll-Schmidt theorem. For those familiar with the representation theory of abstract algebras, you'll have all heard of this theorem, and that's not just a coincidence. What can be shown is that between the representations of certain quivers, and there's a categorical equivalence to the representations of abstract algebras, meaning if we have a representation of a quiver with certain restrictions, then we can find a representation for some abstract algebra. And in this way, we know that the theorems that apply to one field of one of those fields of representation theory are also applicable to the other. But what Kroll-Schmidt theorem tells us is that if we have a quiver Q and a representation M, then M is isomorphic to the direct sum of finitely many indecomposable representations, and that the decomposition is unique up to isomorphism and permutation. So this is important because it tells us that we're not going to be dealing with any infinite structures, which is always nice, and that we know that if we do choose to break it down, we'll only have one possibility up to isomorphism. And so we can take the isoclasses of a quiver, which are the equivalence classes of isomorphic representations, and ask for a given quiver how many of these isoclasses will exist. In other words, if we just look at a quiver, can we tell how many there are? Will there be finitely many or infinitely many? What I showed in my thesis is one of the things is that if we have a quiver with two edges between any two given vertices, either pointing in the same direction, pointing opposite direction, then necessarily there will be infinitely many isoclasses of indecomposable representations. So we can already limit it down to just the quivers that only have at most one edge between any two given vertices. But Gabriel's theorem will provide the important step in determining exactly when a quiver will have finitely many. And so for that, we'll need to know the simply laced Deacon diagrams. And so we have of type AN, which has this linear structure, DN, which breaks off at the end, and then types E6, E7, and E8. Note that if we want to do E5 or less, then it'll be of form DN for some value of it, for N less than 5 or less. And then for E9 and above, while we could form those diagrams and they'd be unique, they don't have the same nice structure as E6, E7, E8 do. There are also the Deacon diagrams for B, C, F, and G, but all of those have multiple edges between two vertices. And so in that case, we won't want to consider those. And what Gabriel's theorem tells us is that a connected quiver contains finitely many isoclasses of indecomposable representations if and only if it is of Deacon type A, D, E6, E7, or E8. So Deacon type means that the underlying graph, regardless of which direction the arrows are pointing, looks like one of the Deacon diagrams of A, D, or E. And we also want to deal with connected quivers just for simplicity's sake, because we could have disconnected quivers that are just two Deacon diagrams next to each other, but that's not really telling us anything special outside of what if we were just looking at one of them. There's also a part 2 to Gabriel's theorem, and that explicitly provides the isoclasses of indecomposable representations for a quiver of Deacon type. So what Gabriel's theorem tells us is we know exactly when our quiver will contain finitely many of these indecomposable representations, and it also tells us exactly what they look like. This theorem is nice because it tells us just by looking at a quiver we can know what the underlying structure is like, whether it has some kind of type of finiteness associated with or if it's infinite. Also, and this is outside of the scope of this presentation, if a quiver is of Deacon type A, D, or E, you can construct something called the Auslander-Wrighton quiver, or the AR quiver, which both provides all of the indecomposable representations as well as a diagram of how they can be mapped to each other. Now we will discuss how this is involved in persistence theory. And so persistence module over some subset T is the collection of K vector spaces for each element of T and linear maps between these spaces such that the following two conditions are satisfied. So the map from a point to itself is the identity, and then the map from I to L is equal to the map from I to J composed with J to L, assuming we have I is less than or equal to J is less than or equal to L. This looks similar to the definition for a quiver representation. That's because if T is a finite set, then a persistence module is over T is equivalent to representation of a quiver of Deacon type A with all the arrows pointing in the same direction. However, a persistence module will not always be a quiver because T can be infinite, and even if T is finite, the vector spaces can be infinite dimensional. This makes notions of indecomposability less certain because we don't have the same, I guess, structure that we can assume with quivers. What we do know is if we have interval decomposable persistence modules, which means that it's either a finite, T is a finite set, or the vector spaces are all finite dimensional, then there exists an index set I and a collection of intervals over I, such that T will decompose nicely, and then we can think of Si as intersections between T and some interval Bi to Di. And then the notation here just acknowledges the fact that it might be uncertain whether our intervals are open or closed. As well, Bi and Bi could be negative at infinity, and Di could possibly be positive infinity. Now, with these intervals, we can create what's known as the persistence barcode, and that's just the decomposition into these intervals. And then the persistence diagram is the multiset, meaning a set that can possibly contain multiples of the same point. And it's all the points Bi to Di for I and I in the extended real plane R2. And we notate it in this manner. And so given a persistence module, we can always construct the persistence, or if it's interval decomposable, we can always construct the persistence diagram. Now, since this is topological data analysis, we want to deal with just general topological structures rather than specifically vector spaces. And so what we can form is a filtration F over a set T in R, and that's a collection of topological spaces that are contained within each other whenever I is less than or equal to J. And then we can also call these a filtration if the intersection is empty and the union is the entire space. Note that if our topological spaces are vector spaces, then we can use the inclusion morphism to get a persistence module. However, our topological spaces might not always be vector spaces. So what we can use are something called homological groups to determine a persistence module from an arbitrary filtration, assuming that the topological spaces are triangulable. And so for a topological, our ultimate goal in this is if we have a topological space F and homeomorphism from F to the real numbers, then we can form a filtration by taking the sublevel sets, which are just the inverse images of everything below a certain point. And our goal is just to determine, using persistence theory, what kind of the structure of these sublevel sets. And so for example, we can take what's known as a point cloud, which is just a set of points. In this case, we'll take ones that are in the shape of a circle of radius r, and the equidistant, and the distance between any two adjacent points we can use c to represent that. And then if we take the distance function, which is just the function from R2 to R that finds in a sense, finds the closest value in our point cloud and then outputs the distance, we can take our sublevel sets. And if you note that the set Pi will be empty if our I is less than 0, because our distance will always be non-negative. And then if our I is less than C over 2, we can kind of think this is all the points in R2 that are less than C over 2 distance, I'm using Euclidean distance here, by the way, less than c over 2 distance from some point on our point cloud. And so that will just provide a bunch of small circles, one around each point. Once we get our distance over c over 2 but less than r, we'll have just one large circular structure with a hole in the middle. And then once our distance is greater than or equal to r, we'll just have one connected component of all the circles just overlapping with each other, and there's no holes. Those familiar with homological algebra should be able to determine what the homological groups are in this situation. But what we can do is show that the persistence diagram for this filtration has this form, where the 23 on this third set indicates that appears in the multi-set 23 times. And then we can compare this to the persistence diagram for a set K, which is just the circle of radius r approximated by p. And that persistence diagram will have this structure. And if we notice, both have this 0 to 0 positive infinity. And then for the second value, we'll have c over 2 to r, or 0 to r. And so the more points we add to this approximation, the closer c over 2 will get to 0. And so the closer p will be to approximating our circle K. And then this 0 to c over 2 will become closer to the origin. And this number, while it will increase, will have that kind of separated from the approximation to the circle. So in this sense, persistence theory can be seen as kind of separating statistical noise from the underlying structure of the data. And that's why it's often used in fields like neuroscience and astrophysics and machine learning and image processing, because it takes a set of data and separates this kind of data noise from the underlying structure, and so that you can see what it looks like when we if we're able to, I guess, determine what the data is trying to approximate.